Hello, and welcome back to Networks Explained Simply. This is video number 3 in our Network Fundamentals series. In our previous videos, we've covered routers, the default gateway, and binary numbers. Click here to check out the rest of our playlist. In today's video, we'll be looking at IP addresses and the subnet mask. When a device connects to a network, it's normally assigned a unique numerical network address, which we call an IP address, and which is used to identify the device on the network. When we use the term IP, we usually mean IP version 4, or Internet Protocol version 4. As the name implies, there are other versions of the Internet Protocol, but as most networks still use IP version 4, that's where we'll keep our focus. A typical IP address looks like this, and we call this format dotted decimal notation. Note that we have 4 decimal numbers, separated by dots, and that each of these numbers can range from 0 to 255. If you're wondering about the reason for this upper limit, stick with us. It will be clear in a few minutes. We can read this IP address in dotted decimal notation as 192.168.1.100. If you take a look at the IP addresses of multiple devices on any network, you might notice that a portion of each device's IP address is identical to the other devices on the network. For example, you might have noticed that your laptop is using 192.168.1.100, while your smartphone uses 192.168.1.114, and your printer uses 192.168.1.150. On this network, it seems that every IP address begins with 192.168.1, and that they differ only in the final number. Having noticed this pattern, we might conclude that the last number in each device's IP address is the only part that matters, since it seems to be the only number that differs. As it turns out, every IP address has 2 sections. The first part identifies the network as a whole, while the last part identifies the host, or the specific device being referenced. We can understand this idea intuitively, just by thinking about the 2 parts of a street address. But unlike a street address, an IP address only contains numbers. So it isn't quite as obvious which part is for the network and which part is for the host, or device. Some networks use a simple scheme like the one we supposed, where only the last number in each IP address differs from the others. But this can vary from one network to another, because it's entirely up to the network administrator. You might be wondering, why would one network be different from another? Is there a reason to choose one way over the other? Let's go back to our example. For this network, we guessed that the first 3 numbers of each IP address represents the network, while the last number represents the host. Remember that the maximum value for each number in an IP address is 255, which means that there are 256 possible values, counting the number 0. So if we've guessed correctly, that means there are exactly 256 unique IP addresses on this network. But another possibility is that only the first 2 numbers represent the network, which would mean that the last 2 together represent the host. Notice that if this were the case, the number of available IP addresses on the network would be much larger, because there are so many unique combinations that can be made with 2 numbers. When planning a network, it's important to provide enough IP addresses to accommodate all of the devices that will use the network, because each device will need a unique address. When a network runs out of available IP addresses, devices will experience connection issues, and users may report that the network is down. On the other hand, having too large of an IP address range can lead to unnecessary complexity, and slower network performance. So when designing a network, the goal is to find a balance that provides enough IP address space for our anticipated needs, but not so much that we cause unnecessary issues for ourselves later. Early IP standards defined several classifications of IP network sizes, and the most commonly referenced of these are classes A, B, and C. These initial classifications were introduced because of their mathematical simplicity, and they were initially expected to be used for most networks. But you might be wondering why there seem to be such huge gaps between these sizes. What if our network needs around 500 IP addresses? Would we really be stuck with using over 65,000? Thankfully, the answer is that we do have more options. This classful system for defining network sizes is still referenced today, but in truth, it's a bit outdated and it's too restrictive for many environments. Thanks to something called classless interdomain routing, or CIDR, we can choose from more granular options. We'll take a closer look at these options in a moment, but first, a quick word about binary numbers. Until now, we've been looking at IP addresses in decimal format, but to go beyond the limitations of classful networks and understand CIDR, we'll need to look at IP addresses in binary format. For viewers not familiar with binary numbers, we recommend pausing the video here. We've published a video on binary numbers, which we recommend watching before continuing to the next section. Use this link to check that out and return to this video when you're ready. With Class A, B, and C networks, the dividing line between the network portion and the host portion of each IP address was always on a dot. Mathematically, this is the reason why we've been able to use decimal numbers up until now, but it's also the reason for the big size differences between the classes. Let's look at this IP address in binary. Notice that in binary, between each dot is a set of 8 binary digits, or bits. Each of these 8-bit sets of numbers is called an octet, and each octet correlates to one decimal number. IP version 4 addresses are described as using a 32-bit format because they always include 4 octets, which is a total of 32 binary digits, or 32 bits. When a decimal number is expressed in binary with less than 8 digits, as is the case with all of our numbers in this example, we simply add extra zeros to the left in order to make a complete octet. We can always add zeros to the left in any number system because adding zeros to the left will never change the value of a number. Earlier, when we discussed IP addresses in decimal, we said that 255 was the upper limit for each number in an IP address. To understand why, let's zoom in on a single binary octet. Remember that each bit has only 2 possible values, 0 or 1. This means that with 8 bits, or 1 octet, the largest binary number we can create is 1111. 1111. If we convert that number from binary into decimal, the value is, you guessed it, 255. So 255 is the largest number allowed in a decimal IP address because it's the largest number that we can make with a binary octet. Let's return to our example network. When we looked at these IP addresses in decimal notation, we made an educated guess that the dividing line between the network and host portions of IP addresses on this network was between the 3rd and 4th numbers. When we compare these IP addresses in binary, we can confirm that the first 24 bits are identical, which tracks with our theory about this network. But if we know that the first 24 bits are identical, then we also know that the first 23 bits are identical, and the first 22. So, in truth, the number of network bits could be any number up to 24. The fact is, we don't yet have enough information to confidently determine the number of network bits that are used on this network. So, what's the additional information that we need? The subnet mask is a setting which is used to define the scope of a network, as well as how IP addresses should be interpreted on the network. Specifically, the subnet mask indicates how many bits in an IP address define the network, which also tells us how many bits remain for the host. Let's take a look at how the subnet mask actually works. The subnet mask uses the same notation as an IP address, with 4 numbers, each between 0 and 255, separated by dots, but with one key difference. Each number in a subnet mask is limited to a specific set of values. Let's look at this subnet mask in binary notation, and let's place it directly under the IP addresses from our example network. How would you describe the pattern of the bit values of this subnet mask? If we read it from left to right, ignoring the dots, what we have is a series of uninterrupted ones, followed by a series of uninterrupted zeros. As it turns out, this pattern is a rule for the subnet mask. When read in binary in its entirety, the subnet mask is always a series of uninterrupted ones, followed by a series of uninterrupted zeros. Here are all of the possible subnet masks shown in binary. Now, here's the same list, but shown in decimal. Next to each subnet mask, we've noted the number of bits in the network portion of the IP address, as well as the number of unique IP addresses which exist on the network. The mathematical function of the subnet mask is that the number of ones in the binary mask defines the scope of the network by providing the number of network bits. As the number of network bits decreases, the number of host bits increases, and with it, the number of unique IP addresses available. For reference, let's label classes A, B, and C. Now that we understand how to use classless network sizes, there's no particular reason to use these unless they happen to be just the right size for our network. A common shorthand method for expressing the subnet mask is to use what's called CIDR notation. Instead of writing out the subnet mask in dotted decimal format, with CIDR notation, we just add a / after a device's IP address, and then indicate the number of network bits, or the number of binary ones from the subnet mask, and that's all we need. This shorthand method allows us to express both the IP address of a specific device along with the subnet mask of the network in one easy step. A common question that comes up for network administrators is whether or not 2 IP addresses are within the same network. Whenever we're asked to determine this about a set of IP addresses, we will always need to know the subnet mask. Without the subnet mask, we can only guess. To reinforce your understanding, we recommend doing some examples on your own. Here are 6 pairs of IP addresses, each with a subnet mask. Feel free to pause the video here, convert the IPs and masks to binary, and then determine whether or not the 2 IP addresses share the same network bits. When you're ready, return to the video and we'll show you the answers. Are you ready? Here are the answers for our examples. In our upcoming videos, we'll be looking at special IP addresses, network address translation, IP address management, and much more. We'll keep all of it simple and easy to digest, so stay tuned. If you enjoyed this video, please remember to like and comment, as this really helps make our videos visible for others. Also, remember to subscribe so you don't miss any of our future videos. As always, thank you so much for watching. We'll see you next time.